Hi, welcome back. My name is Attila Börös. This is the 10th lesson in our solar energy course. In the previous chapters, we learned about the sun, the sunlight, its effects, the history of using the solar energy. In the last videos, we saw how can we convert solar energy to heat energy, and my colleague was talking about how can we convert the solar energy into electricity. The last two times, I started to explain the different solar cell technologies. There are lots of different technologies and still new ones emerge. The solar industry is a quickly developing sector with plenty of new investments and research. I won't try to cover all the solar cell technologies, just most of them which are available today. This is a huge topic, so we need 3 videos to cover them, and this is already the 3rd one and the last in this topic. In the first one, I was talking about the basics of PV cells. We saw how can we link the solar cells, and we started to evaluate the different PV technologies with the most common type. This is the silicon-based solar cell. In the second, we learned about the thin film technologies and the group 3 to 5 PV cells. And as a relaxation, we talked about the loss mechanism in a solar panel. Now, we will proceed on this train of thought and we'll discover the rest of the solar cell types. In this video, we will see the 3rd generation solar cells, and we will talk about some important features of the solar panels. Just in case you get a brochure and you want to compare the different panels in it. You know already this slide. Here are the multitude of solar technologies. On the left side of this slide, you can see the most common group, the silicon cells. The first video in this topic was about them. This group can be further divided to crystalline and thin film silicon cells. These also have subcategories like single and polycrystalline cells. The second big group contains the thin film technology cells like cadmium tellur and CIGC cells, and the group 3 to 5 PV cells like gallium indium phosphate and gallium arsenide cells. That was the second video in this topic about. Today, we will check the 3rd generation solar cells. This group is a continuously expanding one, so we will mention only the more significant ones. The 3rd generation type of solar panels employ mostly thin film technologies that are currently undergoing research and development to make them perfect for the growing solar market. Some of these new age solar panels make use organic materials while some use inorganic substances. Let's see which one I will talk about. I won't explain them in detail, like the silicon solar cells, because mostly they are still in developing stage. I will just mention their most important features and will highlight the new possibilities emerge with using them. The 3rd generation solar cells I will talk about are nanocrystal-based solar cell, biohybrid solar cell, concentrated solar cell, copper zinc tin sulfide solar cell, diasynthesized solar cell, the polymer solar cell, organic solar cell, and color solar cells. Let's start with the nanocrystal-based solar cell. These are generally known as quantum dots. Quantum dots are semiconductor particles, a few nanometers in size, having optical and electronic properties that differ from larger particles due to quantum mechanism. They are a central topic in nanotechnology. When the quantum dots are illuminated by UV light, an electron in the quantum dot can be excited to a state of higher energy. In the case of a semiconducting quantum dot, this process corresponds to the transition of an electron from the valence band to the conductance band. In the right bottom corner, you can see the colloidal quantum dots irradiated with an UV light. Different sized quantum dots emit different colors of light due to quantum confinement. Quantum dot refers to a crystal having small size on the order of nanometers, such as porous silicon. Efficiency of these cells varies from 7 to 8%. These cells have excellent thermal stability and offer a wide range of product design. It is also 50% less expensive than silicon cells and requires less installation time, but larger space. On the right side, you can see the cross-section of a quantum dot solar cell. It has the normal cell structure. It has front and back electrodes, protecting substrate, and also P and N layers. But between them, you can see the quantum dots. Biohybrid solar cell is a solar cell made using a combination of organic matter, photosystem, and inorganic matter. It wants to replicate the photosynthesis. About this, you heard in the third video. Multiple layers of photosystem gather photonic energy, convert it into chemical energy, and create a current that goes through the cell. The cell itself consists of many of the same non-organic materials that are found in other solar cells, with the exception of the injected photosystem complexes, which are introduced and gathered for several days in the gold layer. After days, the photosystem are made visible and appear as a thin green film. It is this thin film that helps and improves the energy conversion. The biohybrid solar cell, however, is still in the research phase. The greatest advantage the biohybrid solar cell has it the way it converts solar energy to electricity with almost 100% efficiency. This means that little to no power is lost through the conversion of chemical to electrical power. These numbers are great compared to only 40% efficiency for traditional solar cells. The cost is also a lot less for producing biohybrids because extracting the protein from spinach and other plants is cheaper compared to the cost of metals needed to produce other solar cells. While the efficiency of the biohybrid cells are much greater, they also have some disadvantages as well. In many cases, some solar cells have some advantages over the biohybrid solar cell. For one, traditional solar cells produce more power than those currently being achieved by biohybrid cells. The lifespan of biohybrid cells is also really short, lasting from a few weeks to 9 months. The durability of the cells proved to be an issue compared to a current solar cell can work for many years. Now, let's see the concentrated solar cell. The system can be familiar from the converting solar energy to heat video. In concentrated solar cell technology, large amount of solar energy is concentrated over a tiny region of a solar cell. The principle of this technology is based on optics. When solar radiations are concentrated on the point, ample amount of heat energy is generated and converted into electricity using integrated power generator. Unlike conventional photovoltaic system, it uses lens or curved mirrors to focus sunlight onto small, highly efficient multi-junction solar cells. They also use solar trackers and even a cooling system, sometimes which enhances their efficiency. However, the CVP solar panels produce their optimum efficiency levels only if they are facing the sun at the perfect angle. This is where the inbuilt solar tracker inside the solar panel comes in handy as it follows the sun. Systems using high concentration photovoltaic possess the highest efficiency of all existing PV technologies, achieving near 40% for production modules and 30% for systems. They enable a smaller photovoltaic array that has the potential to reduce land use, waste heat and material, and balance of system cost. Concentrated PV strength. High efficiencies under direct normal irradiance. Low cost per watt of manufacturing capital. Low temperature coefficients. Additional use of waste heat possible for system with active cooling possible. Increased and stable energy production throughout the day due to the two-axis tracking system. CPV weaknesses. They require frequent cleaning. Highly concentrated PV cannot utilize diffuse radiation, so tracking required. It has limited market, can only be used in regions with high direct normal irradiance, so North Europe is not the best for installing. It cannot be easily installed on rooftops. The challenge of finding alternative solar cells material based on earth-abundant and non-toxic elements prompted the exploration and development of copper-zinc tin sulfide within the thin film PV industry. CZTS is a quaternary compound semiconductor with promising optical absorption properties, a direct band-gap energy of roughly 1.5 eV, and a large absorption coefficient to absorb the most of the visible solar spectrum. CZTS film contains neither rare metals nor toxic materials and can be combined with cadmium-free buffer layer to produce solar cells that are completely non-toxic. CZTS has been prepared by a variety of vacuum and non-vacuum technologies. They mostly mirror what has been successful with CIGG cells. Current higher solar conversion efficiency for solution process CZTS-based solar cell is 10%. For pure CZTS-based solar cells fabricated using a vacuum approach, efficiencies of 8.4% have been reported. Proven record lab cell efficiencies have attained 12.6%. A major technological challenge with CZTS solar cells technology involves the management of cation disorder defects, a phenomenon caused by uncontrolled intersubstitution of zinc and copper cations, resulting into point defects that impede the extraction of charge and decreases the open circuit voltage. A dye-sensitized solar cell is a low-cost solar cell belonging to the group of thin film solar cells. It is based on a semiconductor formed between a photosensitized anode and an electrolyte, a photoelectrochemical system. Of all of solar cell options based on nanomaterials, dye-sensitized solar cells have gained thriving interest and are among the most mature and well understood solar cell technologies. In DSSC, photons are captured by photosynthesizer that is absorbed on a thin layer of nanocrystalline semiconductor placed on the anode. Whereas other PV technologies utilize semiconductors in their solid state for electron transfer for the generation of photoelectric effects, DSSC make use of liquid electrolytes, photoelectrochemical cell, to transfer ions to counter electrode, producing an electric current. DSSCs have attained efficiencies up to 12.3% benefit from their versatility and promising low costs of manufacturing, the use of little quantities of low-cost and readily available materials fabricated by proven processes, simple assembly and flexible modules, compatibility with printing techniques, deposition on various substrates, and integration with a wide range of surfaces. Major challenges with DSSC technology include issues with long-term stability under solar irradiance and high temperature, low absorption coefficients, as well as low open circuit voltage due to interfacial recombination. All these challenges raise the question as to how well they will compete with traditional solar cell technologies, but we will see. Polymers are one of the basic types of engineering materials. They consist of single molecular units called monomers joined up into chains to form polymers. When certain impurities are added to special type of polymer, they can take on semiconductor properties, which is one of the basic properties required for efficient conversion of light energy into electrical energy. A polymer solar cell is a sort of flexible PV solar cell prepared with polymers, large molecules of persistent structural units that generates an electric current from sunlight via the photovoltaic effect. As compared to other solar cell devices, these solar cells are economical, disposable, flexible in nature, and have less impact on the environment. The transparent nature of polymer solar cell results in application, walls, windows, and flexible items. A schematic diagram of a polymer solar cell is shown right side. The cell consists of a transparent substrate, glass or plastic, upon which a thin transparent conducting layer, usually ITU, is deposited. Next comes a layer of the P-type semiconducting plastic, which has a band gap in the useful range and is supposed to absorb photons and create band electron hole pairs called excitons. The excitons migrate, transporting energy but not charge, because they have no net charge, to the heterojunction, where the built-in electric field will dissociate them, the electron being injected into the end material and eventually making its way to the reflecting metal electrode, while the hole remains in the other side and moves to the ITU electrode. An organic solar cell device, or organic photovoltaic cells, is a class of solar cell that uses conductive organic polymers for small organic molecules of light absorption and charge transport. Organic solar cells have become a subject of attention over time due to their prospect for low-cost active materials, low-cost substrates, low energy input, and easy upscaling to the industrial level. They have the potential to provide earth-abundant and low-energy production PV solution. They use small molecules of organic compounds or polymer to absorb light and consist mostly of earth-abundant elements that can be fabricated into thin films using inexpensive deposition methods such as thermal evaporation and inkjet printing. Let's see the pros and cons of them. Advantages: flexibility, roll-to-roll production, low cost and lightweight, easy of integration, ecological and economic benefits. It is semi-transparent. Disadvantages are low efficiency. It has only 5% efficiency compared to the 15% of silicon cells. It has low lifetime, less than 10,000 hours, and it has low yield. Due to the possibility of using various absorbers to create colored or transparent organic PV devices, they are appealing for building integrated applications, personal mobile phone charger, clothes with embedded cells. Lab efficiency of 11.1% have been reported, but at the module level remains considerably lower. Major setbacks include ineffective transport of excited electron hole pairs and charge carriers, poor long-term stability under sunlight, and very low efficiency limits. Now, a few slides about an interesting topic, the colored solar panels. The advantages of colored solar panels are mostly related to aesthetics. Many people find the general look of traditional solar panels to be ugly, and they are therefore reluctant to have them installed on their rooftops. Architects particularly may not want to include them in their design for new buildings. Depending on the color technology chosen, colored solar modules can be blended in with the overall design of a building. On the other hand, they can also be made fun and creative. This way, everyone can find the flavor of solar panel they can live with, even enjoy. Printing images or designs on solar panels is also possible with colored rust. In this case, they can be used for company branding, advertisement, or just for making your building that much more beautiful. When we add color to a solar panel, it becomes less efficient by definition. Some technologies are better at transmitting sunlight through the colored layers than others. Each technology has different efficiencies and often different colors within one technology. It also has varying power ratings. Even though colored solar panels generate less energy than uncolored solar panels, colored modules are simply nicer to look at. This means we can see colored PV modules being installed in places where we otherwise wouldn't want them to be seen, such as building facades. There are three types of solar panel technologies I will talk about: the color glass, the chromatics, and the LOF solar. Color glass modules are monocrystalline solar panels in glass or glass backsheet. The panels are printed with unique ceramic patterns. The ink is deposited in a metric pixel pattern across the surface of the module, allowing light to pass around through the printed shapes to reach the cells. The panels absorb light evenly across its surface, preventing hot spots and maximizing efficiency. The color blast effect has the following properties: high light transmittance. The cells become invisible from a distance of 5 meters. The pattern is printed in color. Colors can be mixed on demand. Each color is printed in a pattern that ensures that the highest efficiency. Darker colors have a higher performance than lighter colors. Images and patterns can be printed. It has an efficiency 75 to 90% of a standard module, 80 to 150 dp per square meter, depending on the color. Chromatics colored solar glass is an opaque glass option for solar panels, which gives the module an even color by hiding the solar components whilst maintaining a high energy generation. Based on the viewing angle, chromatics modules seems to change in color, especially when wet. Chromatics colored solar glass is a Swiss development by Swiss INSO that uses the Morpho butterfly effect to create 6 colors at high efficiency. Cameron Solar's chromatics modules have the following properties. It is possible in 6 colors. Cells are hidden. Colors change with angle of light. It has high power generation. Panels also change color when wet. LOF colored solar cells are typically used in transparent, full glass solar panels to create a sparkling effect on the front with providing shading from behind. LOF colored cells have a lower efficiency than some of the other color options, but grant the opportunity to add color to transparent modules. These colored cells are available in two series, sparkling and matte colors. The Marble series offers 5 high sparkling colors to draw attention to the cells. The Classic series offers 5 matte colors to have the cells blend in with your background. It has 75 to 80% of a standard module efficiency with 80 to 128 VB per square meter. Matte colors produce higher outputs. The Classic matte have fixed color from any light angle, while Marble version has a dynamic experience from changing light. After covering the third generation cell types, let's make a quiz to test your knowledge. Try to find out which solar cell is the question about. Which third generation cell type has almost 100% efficiency but short lifespan? It is the biohybrid solar cell. Which third generation cell type has excellent performance in good radiance conditions but less effective in low radiance areas and require tracking? This is the concentrated solar cell. Which third generation cell type are more economical, disposable, flexible in nature, and have less impact on the environment? This is the polymer solar cell. Which third generation cell type use of liquid electrolytes, photoelectrochemical cell, to transfer ions to a counter electrode? This is the dye-sensitized solar cell. Which third generation cell type has another name as quantum dots, where the semiconductor particles are a few nanometers in size? The nanocrystal-based solar cell. By which third generation cell type has the main goal using earth-abundant and non-toxic elements? This is the copper-zinc-tin sulfide solar cell. After completing the evaluation of the different solar cells, let's see a solar panel datasheet. If you are trying to compare one PV panel to another, it is helpful to understand the key technical parameters or solar panel specifications that impact performance. With this in mind, I have taken some extracts from the specification sheet for a standard polycrystalline solar panel, Honey M plus 265 to 275 watt range, and highlighted key parameters. As you see, there are lots of parameters categorized in two main groups. These are the mechanical specifications and electrical specifications. First, we will start with the mechanical parameters. Solar cell type defines the type of module or cell used in the module. For example, monosilicium, polysilicium, or thin film. This determines the class of conversation efficiency of the module. On this panel, you can see that this is a polycrystalline solar panel with 60 cells in 6x10 grid. Actually, we were talking about that for residential applications, the crystalline silicon cells are almost in monopolistic position. Also, you can remember that monocrystalline cells have rounded edges and bluish appearance, so you can decide which is it from the picture. The next parameter is the cell dimension in inches or millimeters. Defines the size of cell used in the model. This determines the output power of a single solar cell. In this panel, the cells are 156 times 156 millimeters. Module dimension in inches or millimeters. It defines the size of the panel. It determines the number of cells accommodated in the module. As you see here, the dimensions of this panel are 1620 times 992 times 35 millimeters. When we count with the 156 times 156 millimeters cell dimensions, we can calculate the cell numbers and orientation. Across length, 1650 divided by 156 is 10.56. So it means that 10 cells fit in one column. The across breadth is 992 divided by 156 is 6.36. So it means that 6 cells fit in one row. The fourth parameter is the module weight. It defines the weight of the module. This panel is 18.6 kilograms. It determines the maximum number of panels which can be installed. The fifth parameter is glazing or front glass. It defines the type and width of the front glass used. For example, 3.2 millimeters tempered glass. The width determines the strength of the covering. The type of glass used depends on thermal insulation requirements or strength requirements. The sixth mechanical parameter is the frame. It defines the type of the frame used in the module. For example, anodized aluminum alloy, as with this particular model. The frame material is chosen so that it can withstand the environmental effects such as corrosion, hard impact, and so on. Few words about the output cables, which defines the type of cables and sometimes their dimensions provided at output to connect with connector specifications. The rating of the cable is as per rating of the PV module and of optimum length generally required by the customers. This panel has a custom 1 meter long 4 millimeter cable. And the last mechanical specification I will talk is the type of the junction box. It defines the protection level of electrical casing at the back of panel. Also includes the number of bypass diodes it used. For example, IP67 rated with 3 bypass diodes like this one. Before we start the electrical specifications, we should mention 2 different test conditions because in general, both are indicated in a brochure. As you see highlighted there is HTC and NOFTD. But what they mean? We know that the maximum irradiance is 1000 watt per square meter on the surface. The panels are tested once in this optimal case and once with lower and much more realistic conditions. So HTC is the first. HTC or standard test conditions are where irradiance is 1000 watt per square meter, the module temperature is 25 Celsius, air mass is 1.5. Only the mass of the air required here some explanation. This number is somewhat misleading as it refers to the amount of light that has to pass through Earth's atmosphere before it can hit the Earth's surface and has to do mostly with the angle of the sun relative to the reference point of the Earth. This number is minimized when the sun is directly above us the light has to travel a minimum distance straight down. This is practically at noon and on the picture sign big X. And the number increases as the sun goes farther from this reference point and has to go at an angle to hit the same spot. The nominal operating cell temperature, NOCT, is the temperature at which the cells work under a radiance of 800 watts per square meter. At an ambient temperature of 20 Celsius and a wind speed is 1 meter per second. Note that solar cells perform better at lower temperatures, hence the loss in power as cell temperature rises. According to this knowledge, we will check the HTC datasheet to evaluate the electrical specifications. The first is peak power. It defines the maximum power on the panel, for example, 265 watt by the TSM265 and 270 watt by the TSM270 panel. Second is maximum operating voltage, which defines the highest operating voltage of panel at the maximum power at HTC, for example, 30.7 volt. It determines the number of panels required in series. Third is the maximum operating current. It defines the highest operating current of panel at the maximum power at HTC, for example, 8.63 ampere. It determines the wire gauge, used to calculate the voltage drops across the modules or cells. Fourth is open circuit voltage. It defines the output voltage when no load is connected under HTC, for example, 38.5 volts. It determines the maximum possible voltage and the maximum number of modules in series. The fifth electrical specification is the short circuit current. It defines the protection level of electrical casing at the back of panel, for example, 9.1 ampere. It determines the current rating of fuse which is to be used for protection and determines the conductor size. Sixth is module efficiency. Defines the conversion efficiency given by a given module, which is generally lesser than the single solar cell used in the module, for example, 16.2%. This parameter helps in solving the problem of choosing a module. 7. Power tolerance. It defines the range of power deviation from its stated power ratings due to change in the operating condition. It is defined in percent, for example, 0 to 5%. This parameter determines the upper limit for power of a module. We finished the topic, so it's time for a short quiz. Let's try to answer the next few questions. Which parameter determines the strength and the surface area required for installing the panels? It is the module weight and dimension. Which chart would you use for calculations and why? HTC or NOCT? NOCT because it is more realistic. Which parameter determines how many panels do you need to reach the desired power output? The peak power. In the last 3 videos, I tried to describe the different types of solar cells. Most probably, as a citizen, you will meet with the crystalline solar panels in daily use. But as you saw, there are plenty of emerging technologies, so maybe in a couple of years, my previous statement will be wrong. The next topic in our course is the advantages and disadvantages of using solar energy. We will consider all aspects from manufacturing through operation and environmental effect till the destruction of solar panels. Also, you will see some interesting but effective installing places like on water surface, over vegetation, and so on. So see you next time. Thanks for watching. Bye.